In this video, we're going to show you what you need to know in order to do a simple CPU investigation using the PerfView tool. The first step is to launch the tool, and because I'm inside the Microsoft corporate network, I can get that from the CLR main tools share. So I launched the PerfView tool. In addition, I'm going to need some data to look at, and the data that I'm going to look at is this perfdata.etl file that I collected during my last video on collecting PerfView data. This data is about an application called tutorial.exe. To look at the data, all I need to do is double-click on the data in the viewer, and it opens up a bunch of child nodes, and each one of these nodes is a different view of some of the data that's in this file. You can learn more about these different views by selecting one, right-clicking, and selecting the Help on Item menu entry, and that will take you to the documentation on that particular item. You can also simply double-click on them, and that will open that particular view, and you can just see what's in there. And some of the views are self-explanatory, and so that's a fine technique. In our particular case, we're interested in doing a CPU investigation, and so we're going to double-click on the CPU view. The PerfView doesn't immediately bring up the viewer because for the CPU view and a number of other views, you usually don't want to see all the processes in the system. When the data was collected, it's always collected system-wide, and so it's collected data about every process on the system. You probably don't care about every process in the system, so it's using this window to help you select which one you're actually interested in, and we care about this tutorial.exe process. At this point, it's bringing up the stack viewer, and this is the most interesting view in the PerfView tool, and it's well worth understanding well. Like the main view, it has these hyperlinks in various places, and like the main view, these hyperlinks take you to various sections of the help documentation. Moreover, unlike the main view, it has these tabs, and you can learn more about each of those tabs by selecting the little question mark hyperlink. But the most important hyperlinks are these hyperlinks along the top. And that's because they describe things that you really need to know in order to use this view effectively. And you should look at them left to right. So let's start with this one. And this one, this first hyperlink, the Stack View Help, gives you the basic things that you need to know in order to understand what the viewer is at all. But then it quickly segues into this next one, which is a little bit of theory on what the performance data you're looking at actually is. And without this understanding, it's very difficult to, it's very easy for you to make incorrect inferences about the data. And so it is worth reading that. Once you have this theory under your belt, you should be reading this starting an analysis section, and that tells you how to use that theory in order to form a good performance investigation strategy. And then the next hyperlink is sadly one you're going to need at some point or another, which is that at some point things are not going to be working properly, and there are all sorts of little picky details about getting you unstuck or reading the logs that help you diagnose weird problems. And it's nice to know that this troubleshooting information is just one click away. And that's what that's for. And then finally, this last hyperlink tells you about labor-saving tricks you can do, or techniques. They're not even like optional things. They're actually quite valuable things. But the problem is that you won't know about them unless somebody tells you about them. And so I tried to make that a little bit more obvious by having a hyperlink that would put them all in one place so that you could learn about them quickly. So it is, this video is really just the tip of the iceberg in which I talk about a few of the essential things in each one of those views, each one of those hyperlink documentation sections. But what you really need to do is you do need to read those, and I do encourage you to do that. Okay, now that we've gotten that out of the way, I'm going to talk a little bit about the theory that you would have read about if you had clicked on the hyperlink Understanding Perf Data, because you absolutely need to know some things. And in particular, you need to know that when these samples were collected, the way it worked was every millisecond the CPU was stopped wherever it was and a stack trace was taken. And you just did that every millisecond for as long as the program ran. And so this program happened to have run 5,644 milliseconds, or 5.6 seconds. And in that time, 5,192 CPU samples were taken. And so I have 5,192 stacks. And basically what this viewer is showing me is those stacks, those 5,192 stacks. But before I look at those stacks, I need to know that I'm going to get meaningful information out of them. So it's really important that I'm looking at most of my perf problem, because not every perf problem is a CPU perf problem. You might have block time. You might be waiting on the disk. You might be waiting on the network. You might be waiting on some semaphore that some other process owns. If those things happen, you won't be consuming CPU. And all you will see in the CPU view is that CPU that you do use. So unless this number here, which is the amount of CPU, the amount of metric you use, divided by the total amount of time that the program ran, unless that's high, your problem isn't CPU. So in this case, it is high. 92% of one CPU is being used from beginning to end of this process, on average, which is a lot. That means I'm pegging one CPU. Then my problem is probably CPU. But if that had been 0.2 or 0.1, looking at CPU is probably not the right thing to do. So the very first thing that you need to do in a performance investigation is be sure that you're looking at the right data. The second thing you often need to do is you need to make sure that you're looking at the right time range for your data. Now, in this case, we care about the whole time range of the program, so that's okay. But other times you only care about slices. You might only care about startup time and not shutdown time. You might care about only the time when a particular dialog was, when a particular menu entry was selected or whatever. And so you would want to zoom into just that time range. And you can do that with PerfView. That's what all of these boxes are that I haven't explained yet, as well as this when field over here. But we don't need to do it for this the most simple performance investigation, because we care about all of the samples in this process. So what I want to show you is this tree view. So you can see there's a number of tabs, and the tree view tab represents those call stacks aggregated by their prefix to root. So if you will, I have 5,192 stacks that were collected, and of those, all of them started with the root, which isn't surprising, and then some of them were in the process tutorial. And in fact, all of those 5,192 were in that process. And that's, again, by design. We excluded all the other samples. And then of those 5,192, some of them were in a thread, and then some of those were called into NTDLL, into a function that I don't know, and there's this weird other thing going on here with these brackets. And I'm not going to explain this in detail here, but suffice it to say that a whole bunch of frames associated that start with NTDLL, but I have determined that I don't care about, are all folded up into this one node. And so a whole bunch of function calls were in here, but we don't care about those. And eventually it pops out into main, which we do care about. And that in turn, main in turn calls recspin, which in turn calls recspin helper and spin for a second. Both of these, because they're indented the same level, are children of recspin. So this is a tree view, and all I'm doing is and as you can see, is as I go down the tree view fewer and fewer samples. The samples disappear. And this is what's called the top-down analysis, when you start from the root and you say, well, main called these two things, each of which used a certain percentage, and then I look in that one, and I look at that one. And for very simple performance problems, all you have to do is keep clicking the biggest one of these, and you will find your performance problem. And unfortunately, this isn't the simplest case. When I do that, I get down to 18%. 17.3% was being spent in daytime now, which is, noticeable. That's worth going after. But what's interesting is that I lost a large chunk of my time to other things. And that's, in fact, the problem with top-down analyses. If I expand all of the nodes in the tree, I didn't expand all. Expand all. If I expand all the nodes in the tree, you'll see that I actually call daytime now quite a bit. I call it all over the place, but each time I don't call it much. I call it 17% of the time here, 17% of the time there, and so on. So what I really want is, since all of those represent the same function, I kind of want them all grouped together. And that's what a bottom-up analysis does, is group the same function together. And that's what this by name view is about. So when I go over to the by name view, I see that daytime now used 84% of the time, or 4,375 samples were all in daytime get now. I still haven't explained this sneaky other thing. And in fact, that's what's making this analysis so easy, is that all of the samples of everything that daytime now called, it called hundreds of functions inside daytime now. They've all been grouped together and said, you know what, that's all one function as far as I'm concerned. So what I get when I look at a by name view is, if I see something taking up lots of time, in this case 4,375 samples, or 84% of my time, that's my performance problem, or that's my hot area. Now I have two possible issues. It might be because daytime now is expensive, and it might be that it's called a lot. To find out, we need to really look at the source code, and the first way of doing that is I don't want to look at the source code of daytime now. I want to look at who called it. And so what I do for that is I select this node, I right-click, and I say Go to Callers. And you can see there's a shortcut, F10. So if I had hit F10, or right-clicked in that way, I would get those same daytime now, and it would show me those same 4,375 samples, but now I get to see all my callers. I can see that of those samples, 4,368 of them were called from spin for a second, and then 5 of them were called from rec spin helper, and 2 of them were called from rec spin. So obviously, this guy is the one that I really care about. If I were to click into him, I would see that he's called from 2 different places. And, roughly 2/3, 1/3 is being called from one place or the other. So already I'm starting to bifurcate. I'm starting to starting to break up. So really, spin for a second is probably where my performance problem is. So I'm going to right-click on it, and I'm going to go to its source. And so this pops me to the source code for spin for a second. And now I can look at it and determine, is this because spin for a second is being called, is only calling daytime now once, or is it being called a lot, and therefore spin for a second must either being called for a lot of times, or daytime now is really, really expensive. Well, looking at this source code, we can see that what's really going on is that it's being spin for a second is calling daytime now a lot. And so we have found our performance problem, frankly. Our performance problem is that we have this loop that's designed to spin. But let's assume that this was more sane code, and that it was doing its job, the best job it possibly could, and still daytime now was showing up high on my list. if that's true, then I really need to think about optimizing datetime now. And for that, I need to find out more details about datetime now. And I will do that in another video. So to recap, to do the simplest possible performance investigation, you start by simply opening your stacks, picking the process of interest, and then making sure that this number is pretty high. It's pretty high, close to 1, because otherwise it's not a CPU investigation you should be doing. Making sure that the time range that you're looking for is good, is the one you want. And in this case, we wanted the whole process, so that was fine. And then look at this by name view and look at the top entries. That is the essence of a very simple performance investigation. Very simple performance problems, you will find a very hot method, and you just go to its source and you fix it. And you just lather, rinse, and repeat until it's fixed. And that's the simplest now. In other videos, we're going to talk about what happens when I really want to look at what's going on inside datetime now, or what happens when I don't have a great big exclusive time here. I have lots of little exclusive times that I need to somehow, find a big thing to go after. Those are topics for another video. Thank you very much, and I hope you have fun doing your simple performance investigation.